Good morning. Welcome to my talk characterizing graphene oxide suspensions with rheological testing and modeling neutron scattering and the electrochemical performance. Our outline is to quickly go through the motivation objectives, introduce the graphene oxide, discuss a few preliminary results, and then talk about the base rheological constitutive equation known as the enhanced thixotropic M-Hob model. Then we'll talk about the phase of the operation involving rheological data from the Aries G2 rheometer and fitting, and also the interpretation of what that fitting means and what it tells us about the material. And we'll talk about the how the model is robust enough to make very solid predictions. And then we'll talk about our Laus analysis framework series of physical processes. And here we will try to make the determination of if the building and breaking microstructure of the graphene oxide suspension correlates with our metric of solid behavior, GT prime. So this is a depiction of the graphene oxide in the upper left-hand corner and lower right-hand corner. We're showing the aggregates, keeping in mind that in a suspension we have aggregates, the mid-sized characteristic length scale, and then we have the agglomerates, which are little aggregates that are sticking together. And if we go one step smaller than aggregates, we can get down to the actual individual particles. And so we have determined that the graphene oxide, after having undergone 500 G, has hallmark features of any thixo-elasto-visco plastic material, meaning that it does have a microstructure with characteristic timescales of structure breakage and structure rebuilding. We know it has aggregates. We know the aggregates undergo stretching, or the agglomerates undergo stretching before they irreversibly decompose and break down. It also has viscosity. The suspension itself has a backbone by which the individual aggregates and agglomerates are floating around in. And of course, the plastic word refers to this irreversible microstructure change. We have characterized the graphene oxide using cyclic voltammetry and electrochemical impedance spectroscopy to be evaluate its ionic conductivity. It's chemically exfoliated graphene oxide from modified Hummer's method. The graphene oxide is purified through ultracentrifugation at 500 times the force of gravity and resuspended to result in a more homogenous dispersion. So we are going to actively engage with the soft matter characterization tetrahedron. And so here, ultimately, what we're trying to do, and the item that ties the four corners together, is some understanding, some greater understanding of the microstructure. And we're going to do that through constitutive models, traditional rheology experiments, nonlinear rheology experiments, including framework analysis techniques. In this case, we'll use the series of physical processes. And of course, we're going to use small angle neutron scattering and Rheo small angle neutron scattering, all to highlight or elucidate this structure of the graphene oxide material. In our case, it is known that the graphene oxide suspension does conduct electricity. And so the morphology and the concentration of the graphene oxide suspensions, or the aggregates, or the agglomerates, does directly translate into different conductivity levels. So we all started our project by looking at the steady state rheological data on the left-hand side, and we can see that it does have shear thinning behavior. It does appear to have a yield stress on the far left of the stress versus shear rate curve. This is also in figure 2, we see intensity versus Q. And so we can see that there is some interesting scattering and interesting structures formed at about less than 0.01, 1 over inverse angstroms, which led us to believe that this material is ripe for use of the interrogation tetrahedron, soft matter interrogation tetrahedron. This is some data that validates the fact that what we already believe, that it does undergo various changes in conductivity based on suspension and concentration of suspension. Again, some more conductivity testing to validate that this material is ripe for investigation using the soft matter interrogation tetrahedron. And so let's start off by that top corner. We're going to take a series of rheological experiments from steady state, step up and step down experiments, and then we're going to fit a rheological model. We're going to pin down some parameters, and we're going to make predictions of more complicated flows. In this case, it will be oscillatory, small oscillatory shear flow. So our procedure involves fitting the steady state parameters first, locking those in, and then holding them constant while we fit the transient parameters. In this case, we're going to fit those transient parameters to 2 sets of large amplitude oscillatory shear. Once we have established the entire set of best fit parameters, we're going to use those best fit parameters to make predictions on 2 different sets of large amplitude oscillatory shear data. And I just want to highlight that we use the parallel tempering technique to fit the parameters. And this is the formulation of the cost function for steady state on the left and for the large amplitude oscillatory shear on the right. And so we have reached the point in the talk where we have to talk about our thixoelastoviscoplastic modeling. We are using this d lambda dt to model the effects of the microstructure breakage and rebuilding. There is one shear breakage term, and there's 2 structure building terms. Our structure has values of 0 and 1, where 0 is no structure and 1 is fully structured at quiescent flow. On the right-hand side, we see the contribution from the microstructure to the total stress in terms of a viscoelastic ODE. This model is also based on the Maxwell constitutive equation. We have specifically incorporated the White-Metzner approach using a cross model to calculate the viscosity as a function of shear rate. And I would encourage anyone who wants to know more about this MHOB model to check the work of Horner et al. In 2018 and 2019. Overall, we have 5 ordinary differential equations, 6 algebraic equations, 12 parameters, 9 of which are fit to steady state, and 3 are fit to the large amplitude oscillatory shear. And then we're going to use those parameters to predict small amplitude and large amplitude oscillatory shear. Some in the audience may ask, what is large amplitude oscillatory shear? It's a sinusoidal oscillating function of frequency and time with a strain amplitude out front. Taking the first derivative of this gives us the shear rate. In the upper right-hand corner, we can see the viscous projection, which is stress versus shear rate. And the lower right-hand corner, we see stress versus strain, which gives us basically an interpretation of the viscous behavior or the liquid behavior, and on the bottom, the solid and elastic-like behavior. And on the left-hand side, you see the 3-dimensional stress versus strain versus shear rate curve. For small amplitude oscillatory shear, we can recreate the stress signal with the first harmonic, and that is enough to recreate the entire signal. Moving into large amplitude oscillatory shear, we now must incorporate larger and higher order terms, aka the third harmonic. So this is our first fitting. In the upper left-hand corner, again, we pin down the steady state parameters, and then we keep those constant and attempt to fit the best values of the transient parameters using 2 sets of large amplitude oscillatory shear, which are shown on the bottom. On the right-hand side, we see the best fit parameter values and the cost function. And moving forward, we now have pinned down the parameter values, so we're going to use them to predict small amplitude oscillatory shear and the third harmonic intensity divided by the first harmonic intensity. And those are shown in the figures on the left-hand side. The top is the frequency sweep and the bottom is the amplitude sweep. And so this is the result in Lissajous-Bowditch space with the elastic projections on the left-hand side and the viscous projections on the right-hand side. And what we're seeing is inside the black box are the two sets of Laus we use to fit the transient parameters. And inside the red box are two different predictions using the full set of parameters. On the right-hand side, we can see the legend for interpretation of the elastic and viscous projections. Thusly verifying that this is a material that is, number one, viscoelastic and clearly has an underlying microstructure that is undergoing vigorous evolution during a cycle of large amplitude oscillatory shear. And so we want to ask ourselves the question, how does our metrics of structure, in this case we call it lambda, how does that marry up with the elastic and viscous signatures? And so we're using an objective framework called the series of physical processes to analyze the signal. And some of the strengths of SPP are that it incorporates data from every single time point instead of assigning average values over a whole period to allow us to see the evolution of the elastic and viscous-like behavior over a period of Laus. And so this particular mapping allows us to interpret the Cole plots, which you're about to see on the next slide. And really, we can map out things like thickening and thinning and softening and hardening and attempt to marry that up with our understanding of the microstructure. And so this is the case where the frequency is 1 radian per second, the strain amplitude is 5. And what we're seeing on the left is the third harmonic over the first harmonic intensity. The blue line represents the noise floor. Moving from the top to the bottom of the left-hand side, we see that the dashed black line is the Hobb model prediction. The red circles are the data. And so we're looking at the viscous and the elastic projection. On the right-hand side, we're looking at the various metrics from the series of physical processes. In the very first figure shown, we see that this is GT prime, our metric of solid-like inelastic behavior. And underneath it is lambda, or our current value or level of structure. And we can see that as the elastic, transient elastic modulus is peaking, we're starting to show an increase, or at least an almost peak value of the lambda, noting that if you recall that the MHOB model allows for the structure to make contributions also to the total viscosity. So we know that by increasing the lambda, we should theoretically see it happening between the two peaks, one for the transient elastic moduli, one for the transient viscous moduli. Moving forward, we can do the same thing for a frequency of 1 and strain amplitude of 10. And this, at this point on this particular combination of values, we see that the structure is more in line with the elastic signature or solid-like signature, thus verifying that there is in fact an evolving microstructure, and our Laus analysis framework is giving us an opportunity to see into that. Again, we see the same result at the frequency of 1 and strain amplitude of 50. It's thusly verifying that this particular material does in fact have a microstructure. We know it's made up of the aggregates and aggregates as they evolve and then break down over flow. The next phase of the operation is to take this material into SANS, whereby we're going to use small angle neutron scattering in conjunction with rheology, and look how the signatures of the neutron scattering, which in this case is the alignment factor, marry up with not only the rheology but also our TEVP model predictions. Following that, we will try to make a run on Rheo conductivity SANS. And again, at that point, we'll be able to incorporate all 4 corners of the soft matter interrogation tetrahedron. Thank you to our collaborators at University of Delaware, NIST, Dr. Ryan Murphy, Dr. Katie Wygant, and Dr. Paul Butler, and of course, Simon Rogers. Questions?